Right. So let's continue, and so I hope to accelerate a little bit because ultimately we have to come to holography, and we only have 2 lectures left. But of course, you understand that so these lectures is more or less a tool to inspire you to study the subject rather than to convey the full scope of its contents. And in this reference list which you received, you notice that by now there are several books written on ADS-FT correspondence and holography. They are listed one by one. I think 6 or 7, at least 6 books, which means that of course you can find all the relevant information there. If you are interested sufficiently in the subject, which is my job to kind of inspire you to this interest. Right. So so yesterday we started talking about hydrodynamics, and this is relativistic hydrodynamics. We can treat non-relativistic hydrodynamics in a similar fashion, but I won't do it here. So the approach, the modern approach, if you want to hydrodynamics, is to treat it as an effective theory. And effective theory means that we have some microscopic theory underlying our Navier-Stokes equations, and there is some procedure which is not fully understood in all models. How to integrate out to fast degrees of freedom, how to go from the microscopic description of the system to the description which takes only a few degrees of freedom, a few quantities, which are densities of conserved charges, and they adequately describe behavior of water, for example, at scales which are sufficiently large and times which are sufficiently large. In case when you have a kinetic regime in the theory, which we discussed last time, so for example, when you have sufficiently dilute gas or very weakly interacting system, right? So we listed all these criteria, and one of them, I remind you, so this was a rather curious inequality, right? So kinetic theory applied for time scales involved, which were much larger than this interesting quantum time scale, and we will come back to this when we study holography, because holography exactly allows you to penetrate the processes or to consider the processes where tau is of the order of h bar over k Boltzmann T. And this is characteristic of the strongly interacting systems, which is also relevant for things like condensed matter systems and so on. All right, so we had fundamental degrees of freedom. Degrees of freedom, densities of conserved charges. Conserved charges, and here we have a simplest example where the only conserved charge is the energy momentum tensor. So this is the expectation value. Remember, everything without hats will denote expectation value of our operators, and so this quantity is conserved. I can have other conserved charges in the game. So, for example, I can have some conserved current, maybe not one, right? Maybe there are several conserved currents, but for simplicity, I will not consider them here. And the equilibrium state in this simplest situation, so our equilibrium state, we will consider it to be homogeneous and isotropic. Again, just for simplicity, because you can easily imagine that there could be some equilibrium states. So suppose you apply some magnetic field and things are non-homogeneous anymore, or non-isotropic and things like that. So this all can be considered. So what we started doing last time was writing the expression for the expectation value of the energy momentum tensor in a state which is not an equilibrium state, right? So in equilibrium state, in the rest frame of a fluid, it's a 4x4 matrix with epsilon pressure on the diagonal. And now we want to deviate from this equilibrium a little bit, which means that our 4-vector u mu, which was constant in the equilibrium state, now acquires some dependence on 4 coordinates x. So time is included here, right? So now u mu is a function of x, but we assume that, so we just stepped a little bit out of equilibrium. So the dependence of u mu on x is such that derivatives, the gradients of velocities, are not very large. All right, so it means that we are considering, so this requires more detailed discussion what exactly is assumed, but kind of intuitively we understand that we don't want our u mu to change on the scales which are comparable with interatomic distances, right? So it may change, but it may change on a scale which is much larger than, for example, distance between molecules in your liquid, things like that. Okay, but we will try to make it more precise later on. So then why we need this assumption? Because we want to write down what is known as a gradient expansion for our T mu. So we had equilibrium expression for T mu given by, so we split it with respect to this 4 vector u mu in 2 components. One is parallel and one is perpendicular. And the expression had the following form. So here it's P and the projector delta mu, which I wrote last time. I won't rewrite it again. So this is equilibrium situation. And now we want to include also gradients of u mu, right? So this was situation when u mu was a constant. Now we want to include gradients. So how I can include gradients? So this will be done in the following way. I will write down T mu as the derivative of gradient expansion. So formally it will be a series with the index 0, 1, 2, and so on, telling how many derivatives of velocity I will have in each of these ingredients, right? So this index here will denote number of derivatives of u mu. So in T1, I will only have first derivative, meaning d mu u nu, right, with some combinations. And in T2, I can have second derivative of u mu, and so on and so forth. Okay. So what is written here effectively is nothing more. It's a little bit fancy because there are 2 indices, right, involved. But morally speaking, this is nothing but Taylor expansion of your expectation value of T mu. And again, this has a number of assumptions, right? A Taylor expansion, immediately you may worry about the convergence, right? So this is a derivative expansion or gradient expansion. So immediately you may ask, what about the convergence? And the second thing you may ask is it a good assumption that your function can be expanded in Taylor series, right? So are there non-analytic terms and if not, why? And if they're maybe they're suppressed and so on and so forth, right? So these questions, of course, arise, and we will try to address them later on. But so far, let's just build this expansion more or less one by one. Right, so T node is written here, right? This is our T equilibrium. So now, this is the expression which does not involve any derivatives of u mu, just u mu itself. There is nothing else. Okay. Now, how about T1? So T1 u mu is a tensor of the second rank, and it will involve derivatives. So the derivatives will be of the form d mu u nu. But we have to also respect the fact that T mu is symmetric, right? So we need to symmetrize these derivatives, and also it is convenient to split because we have this vector u mu which is an object which breaks Lorentz invariance, and with respect to which we can split any tensor into pieces which are parallel and and orthogonal, right? So just like we did here, right? So the same in the expression for T mu 1, it will be the same game, the same story. I will split it in a parallel and perpendicular piece. All right. It will look a little bit strange, but morally this is exactly what is done here, right? So let me write it down and then I comment on it. So T mu 1 will have two pieces. One is, so there is a coefficient of proportionality, and then there is this projector. Mu alpha delta nu beta, and here you have this gradient d alpha u beta plus d beta u alpha, and I also subtract trace. So alpha beta d lambda u lambda, and then there is a second piece. Okay, let's use minus sign with a different coefficient zeta, and here you have projector and this trace. Okay, so this is everything which involves first derivatives of u mu, and written in the form which splits. So this is a group theory, if you want, right? So you have a tensor of rank k, and you have a preferred direction given by a 4 vector, and you want to split this tensor into irreducible representations according to this chosen direction u mu, right? And then these independent pieces, right? Irreducible representations means that each piece will transform according to appropriate part of the symmetry group independently, right? It will not mix with other pieces, so it's an independent subspace, if you want, of your tensorial space. And the independent subspaces will involve the parallel piece, right? And then there is a transverse piece, and the transverse piece will have the expression of this type, and moreover, we want this piece to be traceless. So we subtracted a trace, and then there is a piece which takes care of a trace, which is a subspace of its own. Okay. So there are two coefficients which enter this expression, and these coefficients are called shear and bulk viscosity correspondingly. So this is shear, viscosity, and bulk viscosity. Bulk viscosity, and the rest are index structures, right? And then there is a velocity u mu. So this procedure can be continued, and then you can write down T mu 2, and this expression is significantly more complicated than this, and I will not write it down. You can find it in the literature in my reference list. But the moral of the story is the same. You will have some pieces of T mu nu now involving second derivatives of velocity u mu, and this piece also can be split according to these irreducible representations of T mu nu relative to u mu. So there will be some structure, some tensor structures involved, and each independent tensor structure will have its own transport coefficient. So these guys are called transport coefficients. Its own transport coefficient multiplying this structure. All right. So let me just schematically say that so there will be some coefficients like so they call tau p, for example, times some structure. Then there is lambda 1 times some structure plus lambda 2 times some structure, and so on, right? So you can analyze all these. And there is also something which is called kappa and others, right? So you can do this analysis. It has been done. And then you can count the number of these coefficients, and you can continue with T mu nu 3 and do the same thing, and so on and so forth. In fact, this process is not completely trivial, and at the moment, what is known is for relativistic hydrodynamics, what is known is the structure of T mu nu 2. So this has been classified completely, and we know how many transport coefficients we have here. But for T mu nu 3, only partial information exists. So it has been written, so all tensor structures were written down with free derivatives, and the number of transport coefficients is something like 64. So it's, it grows with k pretty significantly. But it's not, so there is another piece of analysis which has to be done. So you may wonder if all of these transport coefficients are actually independent. And there are ways to check whether or not they're independent. So in particular, so for first order hydro, for example, you may ask whether the second law of thermodynamics is satisfied. So you can compute the entropy production using these equations. And for example, with T0, you will find out that the entropy is conserved, the entropy is not changing. But here you have derivatives of velocity, therefore you have friction, you have viscosity as a coefficient which describes this friction. So you do have some generation of entropy, right? And you compute the entropy current, and you require, so this computation is done in Landau-Lifshitz volume 5, for example, volume 6, hydrodynamics. And you can look it up, but the moral of the story is that since you require the second law of thermodynamics to be valid at the hydrodynamic scale, then this leads to some inequalities, some constraints on the values of transport coefficients. So, so entropy production being positive leads to inequalities that eta must be greater or equal to 0 and zeta greater or equal to 0. Otherwise, the system is unstable, and we have this violation of the second law. It's one of the things to check. So the same analysis was done for the second order hydro, and this analysis reduces the number of transport coefficients. So if you just analyze tensor structures, you will get, I don't remember exactly the number, but suppose you get something like, well, the order of 100 or maybe 80 or something like that. And then the entropy production analysis reduces this number to, let's say, 64, right? So because not all of them are independent, and they have to obey inequalities of this type. Okay. And equalities also. So for T3, the number of tensor structures is known, but the entropy analysis, entropy production analysis has not been done. And it's a hint. If some of you wanted to kind of immerse yourself into relativistic hydra sufficiently deep, that this is an open problem, so nobody knows, right? So the number of independent transport coefficients at first order is unknown. A relevant problem, related problem is, well, actually, people who did this analysis of tensor structures for T3 are Sasha Grozanov and Nikos Kaplis, and they wrote a computer code because, of course, to deal with these structures when you have thousands of them is very difficult. So they actually wrote a computer code which kind of generates them automatically. And one open question is how many, so can you actually estimate or can you compute how many transport coefficients will appear at order k, right? So let's say number of transport coefficients at order k of derivative expansion. So this is a completely, so suppose this number is n of k. So does it grow exponentially? Does it go like k to some power alpha? What is alpha, and so on, right? So how this scales with the order of hydrodynamic k, it's completely unclear. And this is related to interesting questions of whether or not this expansion is convergent and how you can analyze it and so on, right? Whether you need some special tools to analyze it. Okay. So this is an open problem, and I don't think it's very well. Okay. Another remark is the following. So we wrote all of this in Minkowski spacetime. So we can generalize this to curved spacetime by the usual procedure, by replacing the ordinary derivatives with covariant derivatives, with replacing of Minkowski tensor eta alpha beta with the metric G alpha beta. So of course your velocities now are normalized with this metric tensor alpha u beta is equal to minus c squared, right? So you have to be careful here. And also another piece here is that when you write down all possible tensor structures, if you're in curved space-time, then of course you will have various pieces such as, let's say, R mu nu, R alpha, like things like R mu nu appropriately symmetrized, right? So I'll put this bracket to make it a symmetric combination. So and something from involving, for example, Riemann, let's say mu alpha beta nu, right? And then U alpha U beta. So structures of this type also appropriately symmetrized to respect to symmetries of T mu nu. But the point is that these things, of course, vanish in flat spacetimes because the curvature tensor will vanish. But in general, curved spacetime, they will be there. So when you write down these pieces, right, you write down all tensor structures compatible with the symmetries of T mu nu and involving only k derivatives at order k. Right, that's the only rule that you have to follow. And of course, you have to include terms which contain R mu nu and Riemann and so on in the appropriate power derivatives and so on. All right.
Sorry.
Yep.
In case that you had an equilibrium state that is inhomogeneous, for example,
yeah,
you knew that there is equilibrium, and somehow you knew the T0. Could you follow in a similar fashion?
Yes. So first of all, you have to determine the equilibrium state, right? How T mu nu equilibrium, how T mu nu node looks if you have inhomogeneous state. So for example, you have a magnetic field and something which responds to magnetic field, then yeah, you will have some inhomogeneity, but you can solve the equations of equilibrium and you can write down how T mu nu will look like, right? So for example, you can have situations in which this pressure in Z direction, for example, will not be equal to pressure in X direction, Y direction, right? So that is possible if you have chosen direction, let's say, with magnetic field. Okay, but on top of this, so once you determine the equilibrium state, you just follow the same procedure, right? You have to expand, but now you have to expand not around this state, right?
Yeah,
but around more complicated state. Yeah, okay. Yeah. This can be done. All right, and then you combine. So these expansions are known as constitutive relations. So these expansions are called constitutive relations. And then you combine the constitutive relations with conservation laws, right? So you remember that your T mu nu is conserved, and now you have two equations. One is equation of conservation, and the second one is constitutive relation. And you combine the two. So you write down, so for example, so you combine mu T mu nu, or in curved space-time it will be nabla, right? So equal to 0. So combine conservation law plus constitutive relation at order k, and what you will get is for k equals 0, you get Euler equation. For k equal 1, you get Navier-Stokes. For k equal 2, you get equation which is known as Barnett equation. And as I said yesterday, for k equal 3, nobody knows, so it's up for grabs, so you can derive the equations and it will be named after you. So this is a relativistic case. It is possible to, so I will not write down the equation explicitly. You can do it by just combining these things. And then the next exercise that you can do, and it's useful to do, is to take non-relativistic limit either in those equations or in the constitutive relations, and convince yourself that non-relativistic limit will give you Euler equation, Navier-Stokes equations, and so on in non-relativistic domain, the ones that you usually are dealing with, for example, in volume 6 of Landau and so on. All right. Now, maybe just to make this whole point perhaps a little bit more pronounced, let me just illustrate it again on a simpler case when you have a conserved only conserved current. So similar equations or similar approach can be exercised when you have a conserved current, and in addition to the conserved current, you write down this expansion, right? The constitutive relations, right? So in a similar fashion, and the constitutive relation will start with, so for example, you have a charge density rho, and then in covariant form, it will be rho u mu, and then minus d delta mu nu d nu rho plus higher derivatives. So in the rest frame of the fluid, you will get for the so I didn't put the index, so mu. So for indices k, which are spatial indices x, y, and z, this line here, right? So in the rest frame of the fluid, u mu is 1, 0, 0, 0, right? And therefore, for spatial index, when mu is a spatial index x, y, and z, then you won't have contribution from this term, but you will have contribution from this second term, and this contribution looks very familiar. It will give you just the gradient of the charge density rho, right? So this will give you, and this is known as Fick's law of diffusion. Which simply tells you that if you have a slightly non-homogeneous distribution of charge density rho, then the current will flow from high concentration of charge to low concentration of charge, right? And to linear order in gradients, it will be proportional to the gradient itself. And the coefficient of proportionality is called the diffusion constant, right? So this is 19th century sort of right, Fourier and so on, right? So then you combine, right? You combine combine the conservation law and the constitutive relation, right? And this, if you want Taylor expansion, k equal from 0 to infinity, roughly speaking, right? So that's what it is, right? And then to leading order, what you get is dt rho plus the gradient of rho and plus higher terms, and this whole thing is equal to 0, right? So this is your hydrodynamics at work, right? So the first statement is that fundamental degrees of freedom are densities of conserved charges, statement number 1. So then you have the conservation law for the conserved quantity, right, which is a current. And then constitutive relation is supposed to express, right, if you have a fundamental degrees of freedom, which is a density of charge, here denoted by rho, then you have to express other components, and there are 3 other components, jx, jy, and jz. You have to express through this fundamental degree of freedom somehow. For example, through gradient of this degree of freedom. And this is exactly what is done here, right? So you have to write a second equation. Second equation is constitutive relation, which expresses these extra degrees of freedom, right, jk, through the fundamental degree of freedom, which is in this case only 1, rho. Okay? And this is done via this constitutive relation. So if you combine the two, you will get the equation of diffusion, and then correction to this equation if you include more and more terms in this expansion. All right. So what is done here with T mu nu is a slightly technically more complicated scheme than this diffusion scheme, but morally it is exactly the same. All right. Any questions about?
The energy density only appears in the 0th order, no?
Yeah, the energy density, yes, but the energy density is so here when you write down, so in equilibrium, this epsilon is the equilibrium energy density, right? Once you say that your u mu depends on x, what stands here, right? So what's this coefficient is not the equilibrium energy density, right? It's some scalar which in principle depends on x and t. So with this scalar, you can do the same thing. You can expand it in gradients, right? You expand it in derivatives. The zeroth order term will, of course, coincide with equilibrium energy density, and then there will be some corrections to that. Okay. All right. Fine. So, yep.
So, I mean, why in this? So, I mean, this I would say is less general than, for example, Israel-Stewart theory or something, where you have new degrees of freedom which like have their own evolution equations.
No. This is actually you see. Okay, so.
Because I mean, as I understand, every degree of freedom you identify with some derivative of some other degree of freedom.
That's right.
You basically only have density and maybe velocity.
Yeah.
But
I understand your question. So since you brought up Israel-Stewart, let me. So one question which I try to avoid in this discussion, but apparently it's unavoidable, is. Is the following. You could ask me, so the equations that you are getting, for example, this equation, right, is obviously something which violates causality in special relativity, right? We have a first derivative in time, right? And you can say, fine, so you are dealing with a relativistic system, relativistic hydrodynamics, right? So how about the propagation faster than the speed of light? So here it's perfectly possible, right? You solve a diffusion equation, you have a solution, we all know its exponent, right? It goes like this. There is a signal, for example, at time equals 0, and then a solution is exponential, goes like this, and at any x, no matter how far this x is from the initial source, at infinitesimally small moment of time, the signal is not 0. Right? Once you turn on the source, the solution to this equation tells you that it will be felt anywhere in space, right? No matter how far. So obviously this violates, of course, this limit on the speed of light and so on. You may worry about this compatibility with dealing with relativistic system, but you are violating manifestly the basic principles of special relativity. And the answer to this question is the following. So not really. So you have to keep in mind what kind of assumptions are built in the theory. So remember, this Taylor expansion that we are dealing with is a Taylor expansion in some small parameter which tells us that we only can do it then our signals are sufficiently. So we have changes in our densities of conserved charges over time scales which are sufficiently large. Right, time scales and space scales which are sufficiently large, right? So these are not microscopic scales. So in other words, if you have a solution to the diffusion equation which looks like this, and you worry that you're sitting somewhere here at Alpha Centauri, right, and immediately have a signal once you turn on the signal here on Earth, right, then you can ask yourself, what is the magnitude of this signal here? And the magnitude of this signal here will be much less than interatomic distance. So this whole solution doesn't apply there. The whole scheme doesn't apply there because you only assume that this works at sufficiently large distances, sufficiently large times. Okay, so it's not a violation of special relativity, but on a practical level, when you're dealing with solving equations, relativistic Navier-Stokes equations, for example, then it is a nuisance because you have to deal with this violation of causality all the time. And computers don't like this. So in 1980s, when people were applying this to relativistic astrophysics, this was a problem. And there were some ways to deal with this problem. And ways to deal with this problem is somehow to convert the equations. So the core of the problem is that you have a first derivative in time, right? So you don't have a if you have an equation of motion which contains second derivatives in time, you fine. So there is a finite speed of propagation. You can somehow do it, right? So people introduce various schemes into relativistic hydro in order to deal with this problem. And one of these schemes is called the Israel-Stewart scheme, and it's sort of by hand. It brings some extra degrees of freedom. So you're dealing with hydrodynamic degrees of freedom, right? But of course, your microscopic theory, like water, for example, right? It's not just hydro degrees of freedom. There are more, right? You don't know them because you don't know how to explicitly integrate out your Hamiltonian from H to a level of H2O molecules down to this, right? You don't know how to do it explicitly. But you suspect that, yes, there are some degrees of freedom beyond hydro degrees of freedom. And you can introduce them by hand into the hydrodynamic equations of motion in order to make these equations second order in some kind of artificial fashion, if you want. And this works and this helps a lot. So people like to use Israel-Stewart, but you have to remember that there is some degree of intervention into the scheme, right? So this is a pure effective theory approach which is complete in a sense, right? So you don't have to input anything by hand. Now, however, in holography, when you have actually a tool to access the quantum field theory at these scales, at the hydra scales, and also at microscopic scales, because holography doesn't distinguish. I mean, we don't care. We can treat them on the same footing. I mean, at least we can treat them as a whole set of degrees of freedom. Then you can see explicitly how non-hydrodynamic degrees of freedom, the extra degrees of freedom, which are true in the sense that these are poles of the correlation functions which you compute microscopically, how they enter the game, right? How they emerge as for example, as poles of Green's functions, and in a sense how they justify this approach of Israel and Stewart, which was done by hand, right? But here we have a microscopic theory, and we explicitly see how these extra degrees of freedom appear, right? So that is a very interesting subject. Okay, so now let's compute one of the transport coefficients. So I'll be mostly worried about shear viscosity, and I remind you that we had a tool discussed yesterday, which was called the linear response, and so we use linear response theory. I remind you, I won't write the full formula, but I remind you that there was an operator involved which disturbed our system, and this operator will be our energy momentum tensor operator, and I will choose the spatial momentum q along a z direction, because by assumption my system is completely isotropic, right? So if I have a momentum of my fluctuation anywhere, right, I can always rotate the system so that the z direction coincides with the direction of momentum. Because system is isotropic, I can rotate things as I please, right? So choose this. So then we have the delta of txy, which was the expectation value of in Fourier space, is proportional. The coefficient of proportionality, I remind you, is the retarded Green's function of the component xy of my energy momentum tensor. So this depends on omega and q, and the magnitude of this perturbation hxy, omega and q, right? So where hxy is the metric perturbation, so I write down h mu, I had my Minkowski space, and then I had my perturbation h mu, let's dependent only on time, for example. So with hxy not equal to 0 only, right? So all other h minus are 0. So you have to analyze this a little bit more carefully, whether you can decouple, because when you introduce, for example, perturbation of the metric, you have to carefully see whether the fluctuations with particular polarization, such as xy components, they decouple from any other components of h mu, because otherwise it may happen that some other components will be sourced by your solution for hxy, and this is not. But in this case, nothing else appears, so you can safely put all other fluctuations to 0 and excite only this one, and this is due to isotropy of the system in particular. So, what can we do? So we have this expression from the linear response theory, but we also have the expression for t mu nu, for expectation value of t mu nu, written as a gradient expansion, right? And shear viscosity enters here. And as I said, you can happily generalize this whole expression to the curved space-time. So the only thing I need to do is to replace this with covariant derivative here, covariant derivative here, and g mu nu here, g alpha beta here, right? And covariant derivative here. It will be the same expression now in curved space-time. So fine. So what I want to do is to write down. So for this metric, for this particular metric, I want to write down explicitly what this expansion looks like, right, for component of txy.
Can I?
Yep.
So the derivative I would have taken with respect to the background metric, not the new one. Is that incorrect?
No, the derivative is taken with respect to the full metric.
Including the perturbation.
Yeah. So you have some metric, like you can forget about the split, right? So somebody gives a metric g mu nu, right, and here it is, right? So so let's write this down. So for that we will need to compute these covariant derivatives. So the covariant derivative nabla x acting on uy is dx uy minus Christoffel symbol gamma lambda xy u lambda, and this turns out to be so because the so your velocity is x independent, so you will have minus gamma t xy ut, and this is so u mu, so you convince yourself that u mu remains the same as u mu at rest. So your liquid is the only dependence. So if you have this particular perturbation, the only change will come through the covariant derivatives, through Christoffel symbols of the covariant derivatives, and not through the derivatives themselves. So this is a computation that you can do, that you can convince yourself while doing. And so because this index is lower, right, so we have minus sign. So u mu with lower index is minus 1, 0, with my Minkowski minus plus plus plus. And therefore, this is just gamma t xy itself, right? There is nothing else. And then you compute nabla y of ux, and this turns out to be gamma t yx, which is the same as gamma t xy. And then you compute Christoffel. So for this very simple metric, just a very simple perturbation of the Minkowski metric, the computation of gamma tells you that gamma t xy is equal to 1/2 of the time derivative of hxy. Right? So by standard formulas of general relativity, you can convince yourself that only this Christoffel is non-zero, everything else vanishes. Right? So you have this. Very nice. So now we can substitute, and let me write down the result here. Okay, and production. So what I have is for delta txy, which is txy minus equilibrium value of txy, but equilibrium value of txy, remember this was 0, right? Because our tensor was, our t mu nu was diagonal, have an isotropic system, so so all of diagonal components were 0. So for delta txy, we have the following, now we have the following expression, minus pressure hxy minus 2 eta, so this is coming from this term here, times Christoffel gamma t xy, which we know explicitly, plus high derivative terms, which we don't write. So there are terms which are contained in T2, T3, T4, and so on, and I just denote them as high derivative terms. Of course, this expansion continues forever, but we only worry about the first derivatives of this expansion. Also, I didn't explicitly say this, but you should be aware of the fact that in general, so we assumed here that the expression for T mu nu is the Taylor expansion of our expectation value of T mu nu, or in Fourier space it will be expansion in power, so for example omega, omega squared, omega cubed, and so on. And I warned you that in principle this assumption completely neglects the possibility that there could be non-analytic terms in this expansion. So this expansion may not be an expansion of an analytic function at 0, right? So these non-analytic terms actually do exist. So I will write them like this, and we will discuss them later. Okay. Fine. So now, if I have my with hxy in Fourier space, function of time, e to a minus I omega t, right? And we put q to 0, right? Because we only you can consider more general fluctuations if you want. You can make this h mu depend also on x, right? But it will not bring you anything new as far as viscosity calculation is concerned. So we just consider the time-dependent perturbation of a metric, and therefore q we can take q in Fourier space of hxy being equal to 0. So in Fourier space, this expression for delta txy will look like this. So this is minus pressure hxy plus I omega eta shear viscosity times hxy plus terms of omega squared and higher, which are coming from this piece, plus non-analytic terms, which I didn't explicitly mention. Non-analytic means, for example, omega to power 3/2, right? And so on, 5/2 and log omega and so on. So they do exist, but let's discuss them later. So to lead in order, you have this. And this is this expression just follows from the effective theory expansion for T mu nu directly when you substitute metric of this type. It's nothing more than that. And then you can compare, right? So you have this expression which gives you delta txy, which looks like this, and you have this expression for delta txy, which comes from linear response theory. All right? Now, this is the same as that. If I include here all the terms, because unless I truncate this expansion at order 1, for example, this expansion, which includes also non-analytic contributions, is completely identical to the full quantum field theory expression for the expectation value of T mu nu. There is no approximation, there is nothing. I can truncate, assuming that my omega is small and q is small, right? It means that I kill this whole infinite tail, and I also have to do something about non-analytic terms, but non-analytic terms will only be higher powers. I don't prove it here, but that's a fact of life, and you can show it. They will be powers which are higher than the first power of omega. But if I don't truncate, right, then this delta txy is exactly the same as this delta txy here, and therefore I can equate them. And if I equate them, then I can write down the expression for G retarded. Right. So I compare the two, and I write down G retarded. So G retarded txy as a function of omega, and our q is equal to 0, is just pressure. This is equilibrium pressure minus I omega eta, shear viscosity, plus terms of omega squared and higher, plus non-analytic terms. All right. So, yeah.
I have a question. Till now we have used the quantum field theory part and the perturbation one. and we haven't used the Einstein equation, which relates the perturbation in T mu mu to the metric. Can relate to it.
Oh, we did. We did. Right. Yeah. Because in this expansion here, we wrote it now in curved space-time. Right. So there is covariant derivative here. There is a full metric here. Right. So this expansion is completely generic. I can write it for any fluid, for any gas, for any quantum field theory I want. There is nothing. So this is just a Taylor expansion in curved space-time. Then I choose my curved space-time to be of particular type, right? This particular type is Minkowski space plus a little perturbation, right? H, okay? And I write down what happened to this expansion in this curved space-time, okay? And then I also have a formula, this one, which tells me how quantum field theory, any quantum field theory, would react if I just send the gravitational wave with small perturbation h through it. It will react like this. It will react proportional to this perturbation. The coefficient of proportionality being the retarded Green's function of the operator in question, txy. All right? So I did not specify the theory. It could be any theory. So far, everything is completely generic. Right? And my only conclusion is that if I look, so this function, G retarded, may be extremely complicated function of omega in Q. Right? In some interacting quantum field theory, God knows, it's extremely complicated. But the only thing that I know, right, and this is a conjecture that hydro state exists in my theory, that if I expand this function for small omega and small q, leading order approximation in this expansion must be of the form dictated by hydrodynamics, meaning of this form. I don't know it a priori. It's a conjecture. It means that you take a particular quantum field theory, and if you go to sufficiently large time, sufficiently large space intervals, then you will encounter a regime which is described by hydrodynamics. Right? Maybe, maybe not. In kinetic theory, you can prove it directly. In generic, strongly interacting quantum field theory, it's a conjecture. But it's a plausible conjecture, right? I mean, look at, you know, right. I mean, they do come to a state which is described by hydrodynamics, by and large, right? I mean, it's hard to find a system which doesn't, right? So there is an element of conjecture that this thing must be equal to this with this particular expansion at small omega. Okay. So so if hydro is true for this particular quantum field theory, then it must be that if by some means I can compute my G retarded in this theory, right? So I take my lambda phi to the fourth or QCD or something else, right? And I manage to compute G retarded by, God knows, by some perturbative expansion or some non-perturbative tools, by holography, as we'll do, hopefully. Then I know this expansion for all omegas and all q's. And therefore, I can expand for small omega. Right? And if I expand for small omega, I must find term which is pressure, and the next leading term in omega will be term proportional to shear viscosity. Okay? So the moral of this line is the following, that I can write down a formula for viscosity, and this is just a limit of, I can take the limit of omega going to 0, which kills the whole tail here, and these terms as well. 1 divided by omega, the imaginary part of my retarded correlator of the components txy of txy, the operator as a function of omega, and q equal 0. And this is my operational way to compute shear viscosity in any quantum field theory. So this is known as Kubo formula. Although, so if you kind of investigate historically, it's a rather complicated story. So these formulas were written down in various countries by various people around, from roughly speaking, from 1940s or late 1930s, and mostly in 1950s. So in 1950s and early 1960s, this was really explosion of interest to these matters, and these similar expressions were written in the U.S., in Soviet Union, in Japan, and so on. And so historically, it's different. So Kubo actually wrote different formulas, but yeah. So there were people like Kubo and Mori and Green and Lüttinger. Actually, I think the formula for viscosity, at least in the relativistic context, is first written by Lüttinger. I think it's 1963. There is this fantastic paper in Physrev where, with a footnote by Lüttinger, that because he did it exactly in this way. So he said that we will send gravitational wave. This gravitational wave disturbs the system, right? And then we compute shear viscosity. And there is a little footnote saying that if gravity didn't exist, it should have been invented for the purposes of this paper. So, very modest. Yeah. Well, he could do it. I mean. Fine. So now, finally, we come to holography. So this is just a sketch, right? So I remind you what we did in these lectures so far. We said that we wanted to understand the behavior of n constituents in a certain state, which is equilibrium state and maybe slightly non-equilibrium state. We need thermodynamic properties of this system of a large number of interacting constituents, and thermodynamic properties can be computed if you know Z, partition function. The partition function can be computed either perturbatively, for example, at finite temperature perturbation theory, or non-perturbatively on a lattice, in lattice QCD. But things which depend on time, meaning transport, right? So in situations when you have the actual real-time processes involved, then you can either resort to perturbation theory, it's still fine, so you can use the Schwinger-Keldysh method to compute real-time processes, but you cannot do it on a lattice, right? Because you need Euclidean action in order to have a good, well-defined measure. You can try to do analytic continuation from Euclidean to Minkowski, right, and go back to real time, but because lattice is operating on a finite size lattice space, then it is actually difficult, because for proper analytic continuation you need to know the knowledge of asymptotic behavior of your quantities, and this is usually unavailable from lattice data, and then you have these error bars and so on. It's not completely impossible, it's very difficult to do. And at the moment it's not at the stage where you can do it reliably completely. So then you need some non-perturbative tool in order to compute transport coefficients, right? Perturbatively, you can compute it, right? You can compute viscosity of your QCD plasma, then your coupling constant is very small. You can do this via this complicated perturbation theory at finite temperature. It's possible. But you are interested in the regime of intermediate coupling, where alpha stron is of order 1, right? And you may hope that you can take perturbative methods of which you know only one term, and sort of hope that this answer is not very different from the answer at intermediate coupling. And this, of course, is not even a conjecture. It's a fantasy that your commodity doesn't really change that much when you go from strong coupling to intermediate coupling, which is actually true for things like pressure. Remember, we had this plot where you have this logarithmic descent of the pressure or entropy or energy density from ideal gas values to intermediate coupling, right? So it wasn't that bad. It was about 25% difference between intermediate coupling and ideal gas. For transport, it's very different. For transport, these will be orders of magnitude, or at least one order of magnitude, right? So that's why it's important to have some non-perturbative tools, non-perturbative approach to compute them in a given quantum field theory, if you suspect that the theory is strongly interactive, all right? Great. So this formula tells you that if I know a method of computing two-point functions, for example, of energy momentum tensor in my theory, I know my viscosity coefficient. And I didn't say this, but in fact, so this is known as Kubo formulas, right? So there are many of them, and there is each formula for a given transport coefficient. And one other remark before we go to duality is the following, and this is quite important. So let me perhaps write it here, that because this is something also with open agenda, and you might be interested in it. So we have let me call them green Kubo, right? Maybe more fair. Although I think all of them were derived by Mori, but there is a theorem by Arnold which says that if you have a certain theorem named after a certain person, it's most likely was discovered by somebody else. And this is also true for this particular theorem of Arnold. Right? So so transport coefficients of kth order hydro. So then k is equal to 1. You can extract them from 2-point functions, right, as is shown here, for example. Then k is equal to 2, and you have a so-called second order hydrodynamics. Then there is also a set of Kubo-like formulas which were written down explicitly actually by Guy Moore, who I don't see him in the audience today, but this involves 3-point functions. And presumably this can be continued. Nobody did it beyond this line, but the suspicion is that in fact you can write down something sufficiently generic, and the kth order in hydro transport coefficients, all of them will be related through the k+1 point functions of irrelevant operators, such as T mu nu. Okay, this has not been done, but for this it's known. All right, perfect. Duality. Yeah, so again, so the goal is to have some non-perturbative tool which allows you to compute G-retarded of certain operators such as T mu nu. Okay, that's a goal in the non-perturbative regime in coupling. So we can do it via duality. And so let me say first a few words about duality in general. Too beautiful to touch. So duality so we can view duality as a map, as isomorphism, if you want, between two sets of variables describing the same object. So let me write this down. So the one-to-one correspondence between two sets of variables describing the same object. And what this means, so what kind of object we have in mind? Of course, we have in mind Z, or more generically, we want to think of the generating functional of our Green's function, right? Because I remind you that ultimately our goal is to compute G, retarded or whatever, advanced, or whatever we want. And Green's functions typically, correlation functions are typically computed with the help of generating functional, which is a path integral for some theory. So we have some fields phi. And here, let me write this in Euclidean just to have things better defined. And then there is some current with this operator. And if I want, so these are, so A are parameters of the theory, so some parameters such as masses. And such as mass, temperature, etc. And if I want my correlation functions such as O, right, then I have to take the appropriate number of functional derivatives with respect to J, and I will get my answer. So this is the scheme of things, right? So we need to compute Z, where S, for example, is QCD action, something like that, gauge theory action. So one thing to notice about duality is that, well, we are dealing with an integral here over fields. Now, when you're dealing with an integral in general and you integrate over something like x, right? So let me write down the primitive integral. So a very simple example. Maybe too simple, but nonetheless. So let me write down z of alpha in the form integral from 0 to 1 dx over square root of 1 minus alpha squared x squared. Right, so this is our, and let alpha be in the interval from 0 to 1 for definiteness. So what you can do with this, right? So you have a parameter, dependence on parameter, and then you integrate over fields x. But x is a dummy variable. Just like here, you integrate over phi. Phi is a dummy variable. You can choose a convenient variable. You can make a change of variables in your integral so that your variable becomes a convenient. You reduce the integral to something you already know. Right? This is a standard thing you typically do with integrals. So here you can compute it, for example, perturbatively, right? So you can show that this is, you can expand this square root, and then you happily write down that this is 1 plus alpha squared over 6, and so on. And this works perfectly well. Then alpha is sufficiently small. But suppose you want to know the answer when alpha is close to 1. Right, so then you can change variables. Change variables. You go from x to y with the appropriate. So alpha x is equal to sine y. So of course you have to guess, or you have to see by a very useful method of intense staring and your expression, right? So you immediately notice that this change of variable will do the job. And indeed, if you change variables like this, then z of alpha will be 1 over alpha. Now integral from 0 to arcsine of alpha of this dy, and therefore you happily get the exact answer. And you can show that this is exact solution. And of course you can show that this exact solution in the limit of small alpha gives you this expansion above, right? So the moral of the story is the following, that if you know how to change variables in your path integral in a clever way, so that this path integral becomes something manageable, then you can take it. You can find the answer, because phi is a dummy variable. Who cares if these are gauge fields or some hadron field, God knows what kind of fields. You don't care about this. So this is duality, if you want. So it's a clever change of variables to some other degrees of freedom, right? And these other degrees of freedom, you integrate over them, right? Because you don't care about integration variable, you only care about the dependence on parameters. Okay. Okay. So let me let me give you a slightly less trivial example as an exercise. Just because I'm slightly traumatized by the simplicity of this, so let me. Yeah, right. So the second example is the following. Now consider z of alpha, which is the integral from minus infinity to infinity of the exponent, and in the exponent you have with a minus sign expression of this alpha x plus alpha divided by x squared, exponent close dx. All right. So the exercise for you is to use change of variables, so make change of variables, so change variables. In fact, you need to do it twice for this integral and show and find the answer, right? So answer without Mathematica or any some computer, just by hand, right? So change variables in the appropriate way. Okay, let's for definiteness alpha greater than 0. Right? So just sure. Fine. Now another remark. So we are talking about change of variables, and in fact, you can see in 19th century mathematics how similar structures appear within the Fourier transform. So one example that I wanted to mention is the Poisson summation formula. Summation formula. And the Poisson summation formula tells you that if you have a function, so suppose you have a function which is sufficiently smooth, so suppose this is from C infinity on the line, and you have f hat, which is Fourier transform of this function. So let's say f, let me write it down like this. So f hat of b is the integral from minus infinity to infinity f of a e to the I, and let me put here 2 pi ba with 2 pi for being more convenient. So if this is Fourier transform, then the following formula is valid. So if you sum the function f at integer points n, so where n belongs to z, then this is exactly the same as the sum over k, which also belongs to z of the Fourier image of this function. Okay. All right. So this is something which can be proven in a fairly straightforward manner if you. So it's an exercise for you to prove this, and the discussion of this topic appears in all books on mathematical physics. In particular, it appears in this fantastic set of Courant and Hilbert. So in this case, it's volume 1. So methods of mathematical physics. So there are several books, in my opinion, which must be known to anyone who aspires to be a theoretical physicist, and this two-volume set is one of them. So there's also Morse and Feshbach, but Courant and Hilbert is something that you must read roughly at this stage of your academic life. All right. So why? For example, why Poisson summation formula has anything to do with duality? Well, it does, and the example that they had in one of the lectures is the partition function of the rotator in 2 dimensions. I asked you to derive the explicit expression for it in one of the lectures, and let me write down the answer for this. So you had the partition function z. Let me write down it like this. So z, which was the sum over n in integers, e to the minus pi n squared beta, and beta is inverse temperature. Now you can so this was a 2-dimensional rotator, so ds equal to quantum rotator partition function as a function of beta, right? And you can say, well, okay, fine. So this is not a geometric progression anymore, right? There is n squared involved here. This is Jacobi, one of the Jacobi theta functions, as I mentioned in I think first lecture. But suppose you're interested in asymptotics of this expression, for example, for small or large beta, right? If the beta is sufficiently large, then because of a minus sign, you will see that the first term is sufficient, right? Everything else dies very quickly because it's exponential fall off with n as well. But if beta is small, then it's not obvious, and you have somehow to resum this, right? And this resummation is not obvious how you perform it. But then then you have a Poisson summation formula, and with the help of this formula, you rewrite this as the following expression. So this is 1 over square root of beta. Check this by doing the Fourier transform of this function. It's fairly straightforward. But this is a sum over k now. And you have e to the minus pi, also k squared. K is an integer here. But beta appears in the denominator. It's 1 over beta. So if you think of beta as a coupling constant, it means that Fourier transform allows you to have to go from z as a function of beta to z as a function of 1 over beta, right? So it kind of inverses the coupling. And so here, if you want a strong coupling expansion here, is mapped into weak coupling expansion on the other side, right? And if you know weak coupling perturbative result on this side, it immediately gives you non-perturbative result on this side and vice versa. So this is the simplest example of duality, and it's not an accident that Fourier transform entered this discussion. It's actually has some deep reason for that. The second example of duality, so this is sort of first example. The second example of duality, which I think in general should be known, is so-called Kramers-Vanier duality in lattice statistical mechanics. So let me just remind you. Duality in lattice stat-mech models. So the simplest model you typically discuss in lattice statistical mechanics is the Ising model. It's Ising, not Ising, right? The guy was German, Ising. What do you do, right? So you start, so actually you want something more ambitious. So you start with Hamiltonian, which describes interaction of spins on a lattice. Lattice of maybe a square lattice or some more complicated lattice, but you know that spins is described by Pauli matrices, and here they are. And so sigma I, Pauli. And this is too complicated. So this is known as the quantum Heisenberg model, actually. So this Hamiltonian, this is quantum Heisenberg. And you can discuss this, but you can simplify it as well. Instead of Pauli matrices, you can use scalars. You can think, okay, so let's forget about these complicated 2x2 objects, right? And instead, probably sacrifice sorts. And instead, use a simpler model where you have Hamiltonian of the form minus j, which is a coupling constant, and then there is a sum over nearest neighbor interactions of two scalars, si and sj, where each si takes values only plus minus 1. Very simplified kind of version of spins, but nonetheless, it's remarkably rich. So you can think of a lattice again as a square lattice or more complicated lattice, and these si's are sitting at the sides of the lattice, and they interact with all the neighbors. And then you compute the partition function, and you want to compute thermodynamics and correlation functions and everything else from this model. So the fate of this model is quite interesting. So Ising, actually it's Ising model, but apparently it was actually produced by, it was suggested to Ising by his PhD advisor Lenz, and this is yet another proof of Arnold's theorem, right? It's known as Ising model. So Ising solved one-dimensional Ising model, one-dimensional model, ds equal to 1, solved exactly. solved exactly. And this was, I think, his PhD thesis. Then, so he discovered that Renault phase transition in one dimension and concluded that this model, the Ising model, is not suitable for discussing statistical mechanical properties, right? Because there is no phase transition. And because we were looking for a model of ferromagnetism, of course, and we know that there is a transition to a ferromagnetic state. So his conclusion was that no, this is that doesn't work. So let's think of other models. But that was a little bit too premature. In ds equal 2, there is a phase transition. And it was solved exactly also by, it was solved by Anzager, so solved exactly. Solved exactly. Anzager, 1944. But before solution of Anzager became available, Kramers and Vanier introduced duality in this two-dimensional Ising model and predicted the point of a phase transition. So how did we do this? Yeah, so by the way, the exact solution for ds greater or equal to 3 is unknown, although in recent years there has been a rather dramatic surge of interest to these models in 3 and higher dimensions. And this is related to this conformal bootstrap and all these techniques. I mean, they don't solve exactly the model exactly, but they allow certain methods to predict, for example, critical exponents to some accuracy and so on. And I will not go into this in any detail, but this is kind of a hot topic, and you can look at various papers which involve the name of Slava Rychkov and collaborators. All right. So the duality. So what did they do? So they managed to change variables. They managed to change variables in this Hamiltonian or in a partition function. So let me write down the expression for the partition function. So z we are looking for is trace e to the minus beta h. Right, h is this thing here, and this is sum over all spins taken value plus minus 1. E to the k will be a notation which is just beta times j, right? So this is just a notation. So k, and here we have sum over nearest neighbors I, j, si, and sj, right? So we would like to evaluate this sum, and this eventually has been done by Anzager and various people after him. In fact, Anzager's solution is pretty complicated, and it has been simplified considerably by other people later on. There are several kind of fundamental solutions involving different techniques, which, if you're interested, I can discuss with you in private. But the moral of the story is that you can change, you can rewrite this partition function. You can rewrite this partition function, changing variables, because you see, you sum over all s, just like in the integral, you integrate over all phi, and therefore, these s's are not secret, right? You can change them to any other convenient variable, and if it allows you to compute the sum or simplify your expression. And this is exactly what Kramers and Vanier managed to do. So they rewrote this with some coefficient c. They rewrote this in the form of a partition function. So this was a partition function which depends on k. And they rewrote this as a partition function, which now depends on something called k star, where k star, so this is c of k, and z star is the sum over s star I, taken values plus minus 1, e to the k star, sum with nearest neighbors of si star sj star. All right, and the k star is minus 1/2 log of hyperbolic tanh. Sorry, this is Russified, so let me tanh k. Okay. Now, you may ask, great, so what is a star exactly and how this has been achieved, right? You haven't told us anything, right? So that indeed, this is true. It requires a little bit of work. But essentially, so I won't do it explicitly. This is done in a very good review by Robert Savit, which also enters my reference list. It's an old review, 1980, but it's very, very explicit and sort of pedagogical. So if you want to go, this is fairly straightforward to get from this thing to this thing. So what they did basically, they considered so the dual. So they introduced the dual degrees of freedom. So if you have Si sitting, for example, here at the center of a square lattice, then they were forced, in a way, by the logic of expansion of this exponent, to introduce the degrees of freedom which lived in the centers of the squares surrounding this Si, and these S stars were the Ising variables plus minus 1, which lived in this centers of this dual lattice, right? So you have like this. So there is a one-to-one relationship between, so this is important, there is a relationship between S stars, so S stars of I could be expressed explicitly as functions of S in this case, right? So this is really a change of variables. And again, I'm not doing this explicitly due to lack of time, but it is possible to do. And the important remark is that this transition, this rewriting of the partition function can be understood as a Fourier transform. This has been understood later after Kramers and Wannier, but and in general for any abelian lattice statistical mechanics model, not only for Ising model, this can be done. This duality works, and it is understood as a Fourier transform on the abelian groups. Okay, so this was quite an excitement in the 1970s, 1980s, because of course QCD can be put on a lattice, right, as we know from Marina's lectures and in general, and people wanted to find a duality for QCD on a lattice, right? That would prove confinement and all these wonderful things, presumably. But unfortunately, for QCD, the appropriate symmetry group is non-abelian. And it's not known how to generalize this approach, which deals with Fourier transform on abelian groups to non-abelian case. Right? There are some attempts to do it, but they're not very convincing. So this is another open question. But this is beautifully mathematically sort of well-defined. I mean, this transition here. So I draw your attention to the following fact. So the original, we started with Ising, and we did the change of variables, and we ended up also with Ising in the same number of dimensions. This is not always the case, even in this abelian lattice statistical mechanics duality. You can start with a model which depends on, for example, scalar variables, rewrite this in terms of some dual variables, and these dual variables will not be scalars anymore. They will be, for example, some degrees of freedom which involve some number of indices. And they may not necessarily live in the same number of dimensions. So even in lattice statistical physics, you have this interesting results that when you change the variables, you go to degrees of freedom which are not necessarily the same you started with, right? And moreover, they could be radically different from the ones you started with. Okay? So this is just a lesson. The second lesson is the relationship. So we rewrote this in terms of Ising again, but with a different coupling constant, K star. And K star is related to K explicitly by this equation, which you can, of course, plot. And this is a very instructive and simple plot, which tells you that we are dealing with duality of the Wick-Strand type. So you can actually write this. So this expression for K is equivalent to the following one. Sinh, it's kind of more symmetric and more beautiful. So sinh 2K, sinh 2K star is equal to 1. It's the same as that. And you can plot K star as a function of K, and it will be a function of this kind. So again, you can see, just like in the case of Poisson summation formula, you can see that if you're interested, so suppose you want some answers like correlation functions for the Ising model at very, very large value of K. and you have no idea how to perturbatively calculate these expressions. But you have a dual model, right? A dual expression for the same z, right? Because this tells you that if you have very large k, you have very, very small k star. So you go to k star and you perform your calculation here, and then you have explicit ways to go back to your original variables, right? Like this expression and the expression for s, and you get this at strong coupling, right? So this is a weak strong duality. Weak strong duality. And one immediate consequence of this, which Kramers and Vanier pointed out in their paper, is that if you assume that there is only one phase transition in this two-dimensional system, then the k critical, the k equal to k critical, must obey the equation sinh squared 2k critical equal to 1, which tells you immediately that k critical is equal to minus 1/2 log square root of 2 minus 1, which is approximately 0.4407. So this is a prediction of the critical point, of a critical value of the coupling constant in the two-dimensional Ising model, which was later confirmed by the exact solution of Anzager, who actually got an expression for the free energy explicitly, right? So these people couldn't do it, but they only could predict. This is sufficient for purposes of predicting phase transition point, and it worked very, very beautifully. So, all right. So we have only one lecture left, and that will include all string theory, duality, holography, and consequences of holography for the shear viscosity, right? I don't know how, well, we'll see tomorrow. Right? So. The goal remains the same, right? We wrote today the formula which expresses transport coefficient, one of them, but in fact there are many formulas of this type, namely shear viscosity. Let's focus on shear viscosity through the correlation function of stress energy momentum energy momentum tensor components txy. And now we want to compute this correlation function by some non-perturbative means. So what we are going to do tomorrow is to show that there is a change of variables of sorts in the path integral involving gauge theory of particular type, which allows you to use different degrees of freedom, radically different degrees of freedom, which happen to be involving gravity and black holes and all this stuff, but it's just a change of variable in the path integral, nothing more. All right? And it will allow you to compute the correlation functions, in particular of stress energy tensor, and therefore to get the answer for shear viscosity in the non-perturbative domain. And the coupling is infinitely large, very, very large. So it will be, morally speaking, it will be similar to weak strong duality of the Ising model in the sense that you don't know how to compute viscosity at strong coupling, but you can map it in a different theory where the computation actually tells you, this plot tells you that you can work at weak coupling, therefore perturbatively you can compute everything you need to know. Okay, we'll do this tomorrow. So before lunch, so questions, if you have questions now. Yes, please.
As we know, K has as a coupling has some physical meaning for us in our models, as a strength of some reactions, for example, the couplings.
They do.
Yeah.
Yes. Yes.
Then how can we interpret from going from a small coupling to a big coupling and nothing changes? Then how can we interpret this? Because one of this is measured in experiments for us.
Yeah, so the coupling, of course, is one of these parameters, right? Yeah. So here, for example, now it's a little bit tricky to talk about, for example, coupling in QCD because it's not really a parameter, right? It depends on energy, and therefore, so it's. But let's say for theories which I will discuss tomorrow, life is infinitely simpler. The coupling constant in those theories will be really a constant. It will not run with energy. It will be a parameter which you can put by hand equal to 1000, for example. It will stay 1000 forever. Okay? It's a special class of theories, right, for which these questions don't arise. Now, of course, you're interested in real QCD or real theory, right? And then you ask, well, it's not a parameter, it depends on dynamics. If you change variables, what happens? Yes. So in a sense, one of the reasons why we don't have a gravity dual to QCD, which would be, of course, a desired result of all this business of duality, is precisely because the coupling runs. And you can have a gravity dual change of variables if you want, then the coupling is strong, meaning in infrared of the QCD. But if you go to ultraviolet, and of course in real processes it's very difficult to disentangle, like if you integrate over momenta in some loops and so on, it's very difficult to disentangle sort of infrared from ultraviolet, right, and so on. So, but if you go to ultraviolet, your coupling becomes very small. And then you can hope to have a dual degrees of freedom with change of variables. But we will not include only gravitational degrees of freedom. We will include stringy degrees of freedom, so higher states of strings. And even if in principle it is possible, nobody knows how to, in practice, deal with those degrees of freedom in string theory. If we knew how, we would be able to write down the string dual to QCD with no problem, do the calculation. But exactly, that's a good question. So in many theories, you have really this overlap of these situations, and then you cannot really cleanly kind of disentangle strong coupling and weak coupling, and then it becomes rather problematic. Yeah. Other questions? Right. So one thing that I didn't mention in the Hydra part of today's lecture, but I think it's important to just remember it because of your question, is that you can. So we wrote this expansion of the T mu, of the expectation value of T mu, as a Taylor expansion essentially in omega, and I said that there are also contribution non-analytic in omega. Now these contributions, they come from fluctuations, and to some sense this is similar to looking at the contributions which come from quantum fluctuations in the ordinary quantum field theory. So when you write down the effective action or effective field theory for a certain QFT, then you have to include also the quantum loops, the quantum fluctuations of your fields. So you don't just write the tree-level effective action. So this is in some sense similar to what is happening in hydrodynamics. And if you do this, right, then your transport coefficients, such as viscosity, conductivity, and so on, they will acquire some dependence on energy. Just like, because again, how you look at a typical QFT. You have some operators with some coefficients in front of them, right? Operators are fixed by symmetry, typically, right? But the coefficients, such as masses, charges, and so on, they come from some yet unknown ultraviolet theory, right? By integrating it out, right? Maybe quantum gravity or string, God knows, right? So you integrate it out, you end up with QCD, you end up with QED, and so on and so forth. These coefficients do remember about ultraviolet degrees of freedom, and this memory of ultraviolet. So in principle, if you knew the full theory, including ultraviolet domain, then you would be able to determine these coefficients exactly. But you don't, right? And the memory of the fact that they remember about this ultraviolet behavior and so on is encoded in the values of these coefficients, such as charges, masses, and so on. In hydrodynamics, the analog of these charges and masses are transport coefficients, such as viscosity, conductivity, and so on. So it's natural to ask whether you can write down the renormalization group equation for shear viscosity. And the answer is yes, you can, in the same spirit as you do in quantum field theory by similar tools. Okay? So we are not considering this part, and we are not considering non-analytic terms, in particular because in models in holography, which we are going to discuss, these non-analytic terms will be suppressed by large parameter which happens to be the number of colors. So we will discuss gauge theories with gauge group S, U, and C, and these non-analytic terms, they will be suppressed by power of NC squared. So in the limit of NC going to infinity, these guys can be forgotten happily. Okay? That's why I will not mention them at length tomorrow, but remember that they are there. And in real liquids, in real systems, in non-relativistic systems, these terms, of course, are there, and they were observed and known for quite a long time. Okay, if there are no more questions, then lunch, and we'll continue tomorrow.